Welcome to the Network-Centric Innovation course. In this course, we will look at the relationship between networks and innovation, what networks are, why they matter for innovation, and how to manage network-based innovation. The course is structured of a number of lectures. I will post lecture every other day over the 3 weeks of the course. At the end of each lecture, you will find some homework. I strongly recommend you do the homework. It shouldn't take more than 10 or 20 minutes, but it's important because in this way your progression over the course will be easier. Finally, if you have any questions, please, or requests for clarification or other issues, please post them in the forum section in Moodle. Okay, let's start. The example is about preferences of books. The network represents the books sold in the United States over the summer of 2012 during the presidential election between Democratic Barack Obama and Republican John McCain. The nodes represents customers and the links represents that customers who bought real change also bought economic facts and fallacies. Customers who bought dead, white and blue also tended to buy black belt patriotism, equivalently for the cluster on the left hand side. The red cluster represents books that are sympathetic to the Republican cause, in that case to John McCain. The cluster on the left hand side represents books sympathetic to the Democratic cause. Equivalently, in the blue books, customers who bought shock doctrine also tended to buy recurring crew and so on. Why is this important? This is important because essentially it graphically reveals a common fact in American political and current situation, which is extreme polarization. The graph shows that no customer who bought Republican-leaning books also bought or read Democratic book, and vice versa. So what this network representation is important because it reveals what is hidden in plain sight. It clearly reveals that there are the two large segments of the American population do not talk to each other and do not read the same thing. So by representing who buys what and whether buying one book will lead to buying another book, we basically represent, we can clearly see the polarization of American political current situation. How did we represent this? Essentially by applying the tools provided by a discipline called social network analysis. Social network analysis is a set of tools that allows the representation of a situation, a social situation, by means of a distribution and a configuration of nodes and links. Essentially, who is connected with whom, in this case about book preferences. So this network is an information map that we use to analyze a certain type. The book example we have just given is an example of a network. What is a network? A network, as represented by the technique and the discipline called social network analysis, is nothing else than a representation of nodes and links connecting the nodes. Essentially, any situation can be reduced to can be simplified to a graphical representation of nodes and links. That could be communication system, could be biological system, could be transportation systems, could be geographic systems, could be attitudes, people's attitude, and so on and so forth. Nodes can be anything, can be ants, can be atoms, can be molecules, etc., etc. Links, of course, are connected to what nodes are. So if we're talking about social insects like ants, so links may represent an exchange of information mediated by a type of hormone. If we're dealing with atoms, then a link may represent the sharing of electrons, or the exchange of electrons, or the exchange of some kinds of forces among atoms. If it is a molecule, could be an exchange of sharing of electrons. It could be an exchange of other biological, like electrical signaling. If we're dealing with biological organ, they exchange chemical signals, so a link may represent the fact that there is a sharing or not. If we're dealing with cities, then it could be supply of goods between cities, so a link may represent trading between city. If it is states, it might be whether there's a relationship of war and peace, or economic relations among states. If it is planet, could represent, gravitational forces, etc., etc. So if we are dealing with networks, what we have to do essentially is to identify our agents and represent them as nodes, and then identify the links or the properties among agents that we think are important and that exchange among them, and we represent the flow of information, the flow of goods among our agents that are nodes as links. So essentially, two things: nodes and links. Agents at nodes, links represent exchange of information or a flow among agents. Let me give you 3 examples about networks. The first example is about food chain, essentially who eats whom. See for instance phytoplankton. Phytoplankton is eaten by krill. Krill is eaten by fish. Fish are eaten by penguins. The direction of the arrow goes from prey to predator, from phytoplankton to krill. So this is a graphical representation of the relationship of prey-predator among biological species. My second example concerns a social network, essentially who is connected with whom by means of a certain relationship. Please notice that the link could be directional, so may go from one person to another person, but not vice versa. For instance, this person here has a directional relationship to this other person here, but the relationship doesn't go back. It might be a Twitter situation in which person here follows the other person, but not vice versa. There are also, of course, biunivocal, bidirectional relationship, like the relationship between this individual here and this individual here. Notice that in this way we have a simple representation of a certain type of relationship between individuals over a certain social situation. My third example concerns a geographical representation of a transportation system. In this case, we're talking about the land and underground system. Nodes are stations, underground stations, and links is the path between one station to another station. Essentially tells us whether we can go directly from one station to another station, and also notice that in this case the graph is divided into separate areas that give an indication about how expensive is to go from point A to point B. How do we classify networks? There are multiple ways to do so, and we will look at some of the techniques to classify networks. First, networks can be divided into ordered networks and random or disordered networks. An ordered network is a network whereby the relationship between two nodes tends to be the same. So once we know how nodes are connected, the distribution of links among nodes in a certain area of the network, we can imagine the rest. For instance, in the network on the left hand side, which we call a hierarchical network, we have that the network at the top, say international headquarters, is connected to two further networks, territorial headquarters on the right hand side. The territorial headquarters on the right hand side will be connected to two further nodes, and each of the two further nodes will be connected to other two nodes. For instance, divisional headquarters will be connected to corps and will be connected to social services. We can imagine that this structure will continue on and on. It is hierarchical because information in this case cannot flow directly from, let's say, this node to this node, but it has to go through the path of the hierarchy, up and then down. This is hierarchical network. Unordered but non-hierarchical networks is shown in the right hand side of the graph. In this case, we have that each node is connected to 4 other nodes. For instance, node 4 is connected to 5, is connected to 3, and then it's also connected to 2, and is connected to 6. This situation is repeated over the nodes of the network. So notice, an ordered network in a network whereby the relationship between nodes is given by a procedures that, when iterated, gives the full representation of the network. By converse, a non-ordered network, a disordered network, is, of course, is different in the sense that the number of links among nodes is not constant, and by repeating ascending procedures we do not get the network representation. We may have fully random networks, like the networks represented in the left hand side of the graph, in which we do not see any pattern that help us to reconstruct the relationship among nodes. There are nodes that have very few links, in this case 1 link, and there are nodes at the center that have many more links. There are networks that are random, but we see some patterns, we see some regularities, at least at the statistical level. For instance, if we look at the network on the right hand side that represents airports and flights among networks, so the airports are the nodes and flights connecting airports are the links, we notice that there are certain nodes, like the nodes on the East Coast and certain nodes on the West Coast of the United States, that are disproportionately connected. In this case, we talk about a network characterized by the presence of hubs. Let's analyze networks from the ground up, meaning let's start from the simplest possible network. The simplest possible network is called a dyad, essentially only 2 nodes and 1 relationship. How many different types of relationship we have? Well, in general, a relationship could be undifferentiated, A and B connected without knowing exactly if there is mutuality between the two, or it could be a directed relationship. Say, it could be in Twitter, A follows B, but B may not follow A. It could be a relationship between, let's say, teacher and student. One is the teacher, the other one is the student. So the relationship indicates that there is a direction in it. It could be doctor and patient, so the opposite is not true, or it could be a symmetric relationship. If it is a symmetric relationship, in this case, there's A is connected to B and B is connected to A via the same type of relationship. Friendship is typically a symmetric relationship. Also, there are an indirect type of relationship in which A may be connected to another agent C via the presence of intermediary B. Now, let me give you some important concepts to understand networks. Let's start from propinquity. Propinquity means that individuals or other types of agents are at the same time in the same place. Propinquity is important because propinquity tends to generate links and tend hence to be an enabler of the formation of social networks. If people go to the same school or to the same church or to the same square, they tend to form links and hence they tend to form social networks. So propinquity is an enabler of social networks. It's not necessary to social networks, but if there is propinquity, often we see the emergence of relationships among agents. A very important concept is homophily. Homophily means that homophilous nodes share certain attributes, certain values, or certain characteristics. Homophily may refer to characteristics that are given, like sex or ethnicity or age, or may refer to value homophily, the fact that people who share certain values tend to get together, whether the value is a religion, whether the value is a political preference, or whether the value is liking of a certain artist of a certain type of art. What results is that homophily may lead to the formation of social networks, because people if people are more homophilous, they tend to get together and form networks. So here we have a situation whereby we have a kind of a chicken and egg situation, because if people share certain attributes, they tend to form networks, but if people get together, say in a school, they tend to evolve common attributes that will then result in homophily. So homophily may be at the base of the formation of social networks, but homophily may also result from propinquity, the fact that people growing up together may develop certain common attributes, so they may become more homophilous. Clearly, if you're in marketing, homophily may facilitate, let's say, a marketing policy whereby if your social networks is highly heterogeneous, then the targeting of the marketing policy may become more difficult. So as I said, homophily in general may refer to value or to given characteristics, and homophily may result from the fact that people having certain values in common tend to flock together, but people who happen to be together, they may evolve similar attributes, so they may result in homophilous networks. Finally, another important characteristic, as we have already seen it, is mutuality, or call it reciprocity. Mutuality refers to the fact that what connects two nodes or two individuals is shared by the two. If for instance, a relationship between doctor and patient is not mutual, because it's not reciprocal, meaning that one is the doctor, the other is the patient, and not vice versa. Whereas friendship tends to be symmetrical, meaning A is friend to B, B is friend with A. Let's move one step up in terms of complexity. We have seen what a dyad is: two nodes connected by a relationship that could be mutual or not, or symmetric or asymmetric, directed or undirected. A triad represents three nodes, and the diversity of situations the three nodes may be connected represented, as of course, is much larger. In this case, we have 16 potential relationships. Triads are important because in triads we see the emergence, in a way, of politics. We may have two against one. Triads may form a clique, meaning everybody is related by the same type of relationship within the triads. Let's say if A is friend to B, B is friend to A, and the other two are friends with C, that forms a balanced state. Whereas a triad may be unbalanced because two individuals may like each other, a certain relationship between them, but that relationship may be repulsive or maybe antagonistic toward the third node. So in a triad we have the emergence of balanced or unbalanced situations. In this graph we represent all possible situations of a triad by means of three numbers. The first number gives the number of symmetric relationships, so 0, 0, 1. The second number gives the number of asymmetric relationship. Clearly it is 1 in this case. This is the asymmetric relationship, and it is 0 here. The third number represents instead the number of null, non-existing relationship. Clearly it is 3 in this case, and it is 2 in this case, and 1 in this case. A fully connected symmetrical triad is represented at the bottom right corner of the slides. So as a triad is the foundation of a network. We can represent by a triad some common sociological concepts, like the fact that if A is friend to B is friend to C, A will also tends to be friend with C, or in strategic terms, a friend of my friend is my friend, or an enemy of my enemy tends to be my friend. The first situation is balanced, the second situation tends to be unbalanced. In order to introduce the next concept I'm going to explain, that is density, let's start from a real example. This example represents friendships among individuals attending a karate club. Notice that the graph is can be represented as a distribution of dyadic relationship, 17 connected to 7, 7 connected to 5. Notice that we can also represent the graph in terms of triads. For instance, this is a triad, 6 is connected to 7, 7 is connected to 1, 1 is connected to 6, and so on and so forth. Notice that this is a real network, so tends to be non-ordered, tends to be relatively random, meaning that there's not a fixed relationship of nodes, of relationships among nodes. Notice that certain parts, the central part, is more connected than the peripheral parts. And this leads into the concept of density. What is density? Density is a parameter that characterizes the connectedness of a certain network. How do we measure density? Essentially by dividing the number of actual relationships by the number of potential relationships. In the karate club, there are 156 dyadic connections, but the number of potential connections is over 1000. So the density is 0.139. This is a relatively high number. In most situations, for instance cities, we have a large number of people, but the number of connections that people can manage is about a few hundreds. So that number, density, if we take a city and friendships of individuals in the city, is much lower. So 0.139 is a relatively dense network. In density we have two extremes. The extremes of, let's say, a little village in which everybody is connected to everybody else, everybody talks to anyone else, information flows very quickly in the network. But on the other side, because everyone is connected to everyone else, they tend to have the same information. Whereas in a city, people will have different information simply because they belong to different networks. I close this initial lecture here. In this lecture we have seen what networks are. Networks are a configuration of nodes and links. Nodes represent some type of agents, and links represent a relationship or a flow among those agents. We have seen that links can be directed or undirected, can be symmetrical or asymmetrical, can be reciprocal or not. we have illustrated simplest possible network, that is a diet, and we have moved one step up in complexity and shown a triad. A triad is characterized by the emergence of a balanced or unbalanced state. From there we have looked at the concept of density, the first parameter to actually measure a network, and we have intuitively given some the fact that density is connected with the cohesiveness of a network. It is connected to the diversity of information present in a network. I would like you to do some homework for before the next lecture. Essentially, I've given you some examples of networks. I would like you to look at the examples and answer the following questions. What do nodes represent? What do links represent? Look if there is only one type of nodes or multiple type of nodes. In general, there are multiple ways to answer this question. Then see whether the networks in the examples are ordered or random, they are hierarchical or not. See whether they are hubs, how many hubs. Try to see, in the case of the network 1, the chemical network, how many fully connected triads there are, if any. And finally, in the examples, see which of the following networks show mutual links. The examples are a chemical network, a telecommunication network, and a network citation. Essentially a paper citing other papers. I also offer you a fourth example, which is the evolution of network theory. In this case, see what nodes and links represent. I close this lecture here. I will post